How many spatial dimensions truly exist? Chapter 1. The room with invisible walls. Imagine you're standing in a quiet room. Not a metaphor, an ordinary room. 4 walls, a floor, a ceiling. You can pace left and right. You can walk forward and back. You can jump up and come down. In other words, you can move freely along 3 independent directions. This is so obvious that it becomes invisible. Fish don't notice water. We don't notice dimensionality. Yet tucked inside that unremarkable room is a riddle so deep it has bent mathematics, physics, and philosophy into new shapes. How many spatial dimensions truly exist? If your audiobook needs a hook, here it is. The answer depends on how closely you look, how far you roam, how much energy you spend, and perhaps on how you define exist. It might also depend on who or what you are. Let's begin with a warm-up. What do we even mean by a dimension? In the simplest terms, a dimension is an independent direction you can move without retracing your steps. Draw a line on paper. That's one dimension. Lay down a second line that isn't just a redrawing of the first. Now you have a plane, 2 dimensions. Tilt a third line out of the page. Welcome to space. 3 dimensions. Each new dimension unlocks a degree of freedom that was previously impossible. Squares become cubes. Circles become spheres. Shadows grow thickness. But there's a second, quieter meaning. A dimension is a way to specify where you are. If I pin down your position with coordinates, say X, Y, Z, I have described your location in 3 numbers. If I need 4 numbers or 10, something new is going on. Your room has 3 obvious axes. Our daily lives, our bodies, our architecture, even our language are sculpted by that 3ness. Evolution did not train our eyes to hunt in 10 dimensions or to hide in 2. Our prey and predators lived in forests and plains, not in Calabi-Yau manifolds, and yet we have reasons, good, testable, sometimes tremblingly speculative reasons to suspect that reality is bigger than the room suggests. Before we pry open those reasons, we should meet the most important character in this story, the line between what is and what is useful. A dimension might be physically extended like the horizon in front of you, or it might be curled up so tightly that only particles and experiments of staggering energy can feel it. A dimension might be fundamental, built into the operating system of the universe, or emergent like temperature, a macroscopic concept that arises from collective behavior. A dimension might even be an illusion, a trick your equations play because they're trying to keep a secret. With that caution in pocket, step out of the room with me, the Flatlanders, and us. To glimpse our blind spots, we meet the Flatlanders, imaginary creatures who live on a sheet of paper. They know only 2 dimensions. A circle is a home, a line is a fence, up is a forbidden word. If you poke a finger through their world, they witness a miracle. A small circle appears from nowhere, swells into a ring, and shrinks to a point before vanishing. A Flatlander priest might call it a visitation. A Flatlander scientist, braver and humbler, might propose a 3rd dimension they cannot see. We are the Flatlanders of the 3rd dimension's older cousin. If there are extra spatial directions, we feel them only in indirect ways. They might leak gravity, tweak particle masses, or whisper at the edge of our detectors. The visitations, if any, would be subtle, a tiny deviation in how gravity weakens with distance, a peculiar energy threshold at the Large Hadron Collider, an anomaly in the cosmic microwave background. The trick is to decide which miracles are physics and which are just noisy instruments. A universe that bent time. The first blow against our common sense came not from extra space but from a stitch between space and time. In 1905 and 1915, Einstein revealed that what we thought were separate fabrics, where we are and when we are actually threads in a single tapestry. Spacetime, for motion at speeds near light, the when mixes with the where. This didn't add a spatial dimension, but it changed the character of dimension itself. We learned that what you measure depends on how you move. Coordinates are not the cosmos. They're just the labels we pin on it. Then, in 1919, the bending of starlight during a solar eclipse flipped a switch in humanity's mind. Space isn't a rigid stage where matter dances. It is a flexible partner. Mass and energy curve space-time, and free-falling objects follow those curves. You and I learned this as gravity falling apples. Einstein taught us to see geometry. That geometry, on large scales, is astonishingly smooth and three-dimensional. The cosmos expands, galaxies sail away, light redshifts, but the number of extended spatial directions you need to chart the voyage is 3. If there are more, they hide. A fourth direction that wasn't time. Just after Einstein, Theodore Kaluza had a bold thought. What if Maxwell's equations of electromagnetism and Einstein's equations of gravity are two faces of a single geometry, provided you sneak in an extra spatial dimension? Oscar Klein then suggested why we might have missed it. The extra direction could be curled into a tiny circle, so tight that human eyes or even microscopes could never trace it. The idea was wild and beautiful. It also predicted nothing we could measure at the time. Kaluza-Klein theory became a prototype, a parable about how extra dimensions might be real, compact, and shy. The room had a hidden alcove, but the door was smaller than an atom. The string quartet and their compact stage. Fast forward to the late 20th century. Particle physics had charted the standard model quarks, leptons, bosons, a triumph that still stands. Gravity, meanwhile, refused to come quietly into the quantum fold. String theory offered a truce. Perhaps particles are not points, but vibrating strings. Different modes of vibration correspond to different particles, the way different notes emerge from a violin string. But the math of strings insists on a bigger stage. 10 space-time dimensions for superstrings, 9 spatial, and 1 time. 11 for its mysterious sibling M theory. Why so many? Because consistency, quantum coherence, plus supersymmetry, plus freedom from mathematical anomalies demands room to breathe. In these theories, the extra dimensions are not optional decorations, they are structural beams. Without them, the building collapses. Where are those extra spatial directions? The standard answer: compactified. Imagine each point of ordinary space concealing an intricate, 6-dimensional shape, a Calabi-Yau manifold curled so tightly that only particles with energies near the Planck scale could resolve them. The way that manifold folds and twists sets the tuning of the universe. Particle masses, coupling strengths, even the count of particle families might echo the topology of unseen dimensions. It's a breathtaking picture music written in geometry. It's also a promise we haven't yet forced the universe to keep. How to look for what's hidden. If extra spatial dimensions exist, they can betray themselves. Gravity, for example, weakens with the square of distance in three-dimensional space. If you add large extra dimensions, large by microscopic standards, the weakening law can change at tiny separations. Physicists have built exquisitely sensitive torsion balances and micro-cantilever experiments to test gravity down to fractions of a millimeter and even smaller. So far, Newton's inverse square law holds tight at those scales. If extra dimensions are there, they are smaller than our current reach or interact more coyly than our designs anticipate. Colliders offer another route. Accelerate particles to colossal energies, smash them together, and sift the rubble for patterns that don't belong. Heavy Kaluza Klein excitations particles, revealing the discrete momentum steps you get from motion around a tiny circular dimension, could appear as bumps in the data. Or energy might vanish into the bulk, into gravitons escaping our brain into surrounding dimensions, leaving a missing momentum signature. The detectors are silent on this so far. The sky itself is a laboratory. The early universe was a furnace hot enough to sample deeper layers of reality. If extra dimensions distorted gravity or the quantum foam at primordial scales, their fingerprints might linger in the cosmic microwave background or in the distribution of galaxies across space. Analyses continue, surprises remain possible. The prevailing map still reads 3 large spatial dimensions. When dimension isn't a number, but a behavior, let's step sideways. Not all dimensions are the how many axes you learned in school. In fractal geometry, the dimension of a rough coastline is not 1A line, and not quite 2AA plane, but something in between, say, 1.26, depending on how you measure. That number describes how details proliferate as you zoom in. Physicists studying quantum gravity sometimes adopt a similar idea. The spectral dimension, defined by how a random walker explores spacetime, can change with scale. In certain approaches, causal dynamical triangulations, asymptotic safety, the effective dimension of spacetime might flow from 4 at human scales down to 2 at the Planck length. This is not the same as hidden extra rooms. It's more like the walls themselves, changing texture as you get close. The universe might be multi-dimensional, not because there are many directions, but because dimension itself is a scale-dependent property. Then there's emergence. In condensed matter physics, collective behaviors produce new dimensions of description. Consider the strange metals and quantum Hall systems, where low-energy excitations look like particles living on fewer or more effective dimensions than the underlying crystal. Or think of a fluid. Pressure and temperature are not written into any single molecule. They are macroscopic, emergent. Some theorists suspect that space and even time might be like that. Not fundamental objects, but emergent from entanglement, from the way quantum information knits together. If that's true, then asking how many spatial dimensions truly exist is like asking how many dimensions does a mirage have? The answer might be as many as the pattern needs. The holographic hint. The holographic principle proposes that the information content of a region of space scales not with its volume, but with its boundary area. In certain models, de Sitter space with a conformal field theory on its edge. The physics in a bulk volume with gravity is exactly equivalent to a theory without gravity living on a lower dimensional boundary. Bulk geometry emerges from boundary entanglement, like a 3D image from a 2D plate. This is not a fairy tale. It's a working dictionary that has solved real problems in strongly coupled quantum systems. But as a guide to our universe, it is a parable with a caveat. Our cosmos does not appear to be anti-de Sitter. It's closer to de Sitter, with a positive cosmological constant. Still, the moral survives. Dimension can be a bookkeeping device, a change of variables, a way the universe decides to compress its secrets. If a world with gravity can be equivalent to a world without it on a lower dimensional stage, then spatial dimension may be less a count of hallways and more a choice of language. Life in 3. Amid these grand speculations, daily life keeps us honest. Chemistry works in 3 dimensions because the inverse square law of electrostatics stabilizes atoms and molecules. Planetary orbits are stable in 3 dimensions, but misbehave in higher ones. The inverse square gravity we actually observe allows complex structures, solar systems, galaxies, ecosystems to persist. If you're searching for a cosmic anthropic footnote, you might be tempted to say, of course we live in 3 extended dimensions. In 4 or 7, life like us would struggle to take root. But that's an argument about our branch of reality, not necessarily about the roots. The empirical fact remains. On scales we can see and touch and measure with exquisite tools, space offers 3 extended spatial dimensions. The ways we arrange furniture, launch rockets, write GPS software, and design concert halls all exploit that 3-fold freedom. If there are other directions, they don't help you parallel park. The quiet experimental verdict. So far, it's tempting to fill the gaps with metaphysics or poetry, but let's be stubbornly sober for a moment. Precision experiments have looked for deviations from inverse square gravity down to sub-millimeter scales. None found a crack large enough to squeeze a macroscopic extra dimension through. Particle colliders have probed the TV frontier, hunting for missing energy or resonances that would shout, Kaluza, Klein. Our detectors heard ordinary particle physics and the static of statistical fluctuations. Astronomical surveys have weighed how gravity sculpts structure across billions of light years. The data, while open to nuance, sing mostly in 3-part harmony. These are absence of evidence statements, not evidence of absence, but they are not empty. Every null result tightens a bound. Every bound narrows the plausible architectures of hidden space. If extra spatial dimensions exist, they are small by human standards, warped cleverly, confined by fields to a thin 3-dimensional brain, or emergent in ways that elude direct visualization. What do we mean by truly? We've been quiet about a word hiding in plain sight. Truly, how many spatial dimensions truly exist? The adverb is a trapdoor. It plunges us from physics into philosophy. If truly means could, in principle, be measured by some conceivable experiment within the laws of nature, then the answer is a research program. You set sensitivities, design instruments, write proposals, dream bigger accelerators, better interferometers, longer baselines. Under this definition, dimensions that never couple to any field we can excite are fictions useful, perhaps in equations, but not in nature. If truly means participate in the most economical, internally consistent description of all observed phenomena, then the answer is a judgment call. Today, 3 extended spatial dimensions plus whatever emergent or compact machinery best unifies quantum field theory, and gravity would win. But we don't yet know that machinery. The jury is still wandering the library shelves. If truly means appear in the deepest, most elegant laws from which everything else follows, then we must first locate those laws. We are not there yet. The whispers from holography, the songs from strings, the sketches from loop quantum gravity and asymptotic safety and causal sets, they're promising languages. We're learning the grammar. We don't yet have the final poem. The Room Revisited. Let's return to the room. Its walls did not move while we traveled, but you did. You learned that 3 is a robust empirical fact at human scales. You learned there could be more, curled or warped, that only gravity or high-energy probes can feel. You learned that dimension can be effective, spectral, emergent, an idea that changes flavor with context. You learned that sometimes the world tricks us. A fully 3-dimensional experience can be encoded on a 2-dimensional surface, and a theory without gravity can reproduce a world with it. You learned that the question, how many, might have more than one honest answer, depending on the rules of the game. And you learned caution. The universe loves to surprise. The last century liberated us from the tyranny of common sense. The next may liberate us from the tyranny of our current metaphors. In the second chapter, we'll stalk the frontier where hypotheses become data. We'll examine the map of constraints drawn by tabletop gravity experiments, collider searches, gravitational waves, black hole thermodynamics, and the cosmic background's faint modeling. We'll explore how extra dimensions, if present, could solve old puzzles, hierarchy problems, flavor mysteries, and how emergent dimensions may thread spacetime from quantum entanglement. We'll also face the hard possibility that 3 is not just practical but final for space, and that the richness beyond it lives not in more directions but in deeper structures. Finally, we'll come back to the word truly and attempt a verdict, one honest enough to satisfy a scientist and vivid enough to satisfy a storyteller. For now, stand in your room, stretch out your arms, turn, step, leap. You are a creature of 3 vast directions and 1 relentless time. Your heart keeps count in beats. Your brain navigates in angles and distances. But don't be fooled by comfort. Somewhere in the quiet between plank floorboards, in the hum of pipes inside the walls, in the quiver of air above the radiator, other possibilities murmur. The house of reality may have more rooms than we know, some tiny, some only blueprints, some reflected in a mirror we haven't yet polished. And if we're patient, courageous, and a little lucky, we might find a door. Chapter 2. The map, the territory, and the edges of the page. Let's put our hands on the instruments. The first chapter walked the corridors of ideas. This one checks the locks, shakes the doorknobs, peers through the keyholes that experiments have opened. Because when you ask how many spatial dimensions truly exist, you are, in the end, asking for leverage. Where do we push the world so that it pushes back with an answer? Think of a violin maker tapping a plate of spruce and listening for the note. Physics is the art of tapping the universe in clever, sometimes roundabout ways, and reading the resonance. Our question, once it leaves the realm of speculation, becomes, where do extra directions, if any, change the tune? The inverse square lullaby. Start small. Gravity, at distances we can test, hums an inverse square lullaby. Double the distance, and the pull drops to a quarter. That power too whispers the count of extended spatial dimensions. In a space with him and in spatial dimensions, A point source spreads its field over an 1 is 1 in a one-dimensional sphere. The flux thins as 1 and Barton is 1. 1 divided by r, n1. The fact that pendulums and planets obey 1 and 2. 1 divided by r, 2 is the signature of 3. So, experimentalists have tried to break the lullaby. They use torsion balances, delicate dumbbells of metal on fibers thinner than a hair to compare pulls at different separations. They sculpt tiny test masses with drilled holes so that Newton's law, if slightly wrong, would produce a measurable twist. They suspend micro-cantilevers and push them with patterned gravity fields the size of grains of sand. Every setup is an attempt to create a vacuum for doubt, a chamber where the only whisper left is gravity's. The result? The curve stays inverse square down to distances smaller than a human hair, smaller than a dust mite, down into microns. That doesn't kill extra dimensions, it fences them. If there are additional directions, they either hide beneath those scales or they shape gravity so subtly that our taps are too gentle to disturb them. The violin sings on pitch. The 2 extra room blueprints. 2 blueprints dominate the imagination about how extra dimensions might both exist and remain invisible to our senses. The ADD model and the Randall-Sundrum models. You can think of them as architects that took Kaluza and Klein's old bungalow and added secret rooms with modern tricks. ADD Arkani Hamed, Demopoulos, Diwali proposed large extra dimensions by the standards of particle physics, perhaps as wide as a fraction of a millimeter. All the standard model fields, the particles that make matter and light, are confined to a 3-dimensional brane, a sheet floating in a higher dimensional bulk. Gravity alone wanders the bulk, which dilutes its strength in our brain, explaining why gravity feels absurdly weak compared to electromagnetism. The upside? If those extra dimensions are truly that large, experiments should see deviations from inverse square gravity or production of gravitons into the bulk at colliders. The downside? Precision tests have pushed the sizes smaller and smaller, and the colliders have found no convincing footprints. Randall-Sundrum models went a different way. Extra dimensions can be small, yet profoundly warped. Visualize a rubber sheet stretched tight in some places and pinched in others. Warping changes how distances and energies translate. It can also explain the hierarchy between the electroweak scale and the Planck scale. The warped extra dimension acts like an amplifier or attenuator. Here, the signatures would be different. Massive resonances, Kaluza, Klein gravitons, with distinctive decay patterns and modified gravity at certain energies. The hunt continues, but the easy candidates have slipped away. Why do these models matter for our narrative? Because they make how many spatial dimensions exist a quantitative proposition, not just a philosophical inversion, but a list of hard predictions. How many Kaluza-Klein steps? At what energies? With what branching ratios? Where do you place the brain? What's the warp factor? Translation: build detectors, watch for bumps, trust your statistics. The collider as oracular stone. Particle colliders are story machines. They smash the past into the present and ask the future to interpret the pieces. If the world has extra spatial dimensions that standard model particles cannot roam but gravitons can, then one of the cleanest signatures is missing transverse energy. 2 protons crash. The debris squirts out, and some of the energy vanishes into a direction our brain-bound detectors can't see. The leftover pattern, the balance of jets and leptons and photons, tells you something left the building. Colliders have also hunted for resonant states that would be the Kaluza Klein modes, the discrete momentum levels you'd get by wrapping motion around a tiny circle. If that circle has a radius, r, then momenta in that direction come in steps of might. 1. Here is 1 divided by r. Those steps show up as particles with specific masses. A bump in the invariant mass distribution is the collider's version of a ringing bell. What have we learned? No clear bells. The halls of CERN are efficient at ruling out ghosts. If there are Kaluza-Klein gravitons, their masses, couplings, or the spacing between modes must lie outside the ranges already swept. The oracular stone has spoken the most frustrating kind of truth. Not yet. But also remember that colliders speak a second language, indirect constraints. Even if new states are too heavy to produce, they can perturb processes via virtual effects, shifting the probabilities of familiar decays by a tiny amount. Precision fits to electroweak measurements have become an art form, and they make it harder for extra dimensions to hide. If additional directions are out there, they've learned to whisper through the noise. The sky as detector. Long before we built colliders, the universe ran one for us. The early cosmos was so hot and dense that it churned through states and energies beyond our industrial dreams. When space cooled, it kept the receipts. 3 categories of cosmic receipt matter to our story. First, the light. The cosmic microwave background photons last scattered when the universe was 380,000 years old, carries in its temperature ripples a map of primordial fluctuations. If gravity had behaved differently at early times because extra dimensions modified its strength, the spatial pattern of hot and cold speckles would shift. Analysts run thousands of models against those speckles and carve away possibilities broadly. 3 extended spatial dimensions with Einstein gravity does a superb job. Variations must be small and cunning. Second, the growth. The large-scale structure, the way galaxies cluster, filaments thread, and voids yawn, is gravity's cumulative sculpture. Extra-dimensional tweaks to the force law would alter the pace and scale of collapse. Surveys have measured the power spectrum of matter fluctuations across a range of redshifts. Again, the fit's like the standard 3-dimensional recipe. There is wiggle room. There always is. But the room is not a ballroom. Third, the clamor. High-energy astrophysics, supernovae, gamma-ray bursts, neutron star mergers, probes how efficiently the cosmos can leak energy into channels we cannot see. If gravitons could sprint into extra dimensions, the cooling of hot, dense objects would have been faster. The shape of explosive events would change. Detailed modeling compares theory and signal. So far, extra-dimensional channels are either tightly pinched or weakly coupled. The folded chalkboard. Black holes and entropy. Black holes are both nightmare and dream for dimensional arguments. They are, if you'll forgive the metaphor, folded chalkboards. Anything you write on them is stored on the surface. The area scaling of black hole entropy is the start of the holographic principle. The number of microstates that fit in a region scales with its boundary area, not its volume. If you let that idea breathe, you arrive at a suspicion that haunts modern theory. Perhaps spacetime and its geometry are bookkeeping for quantum information. That suspicion has teeth. In a particular playground anti-de Sitter space at S, there is a precise dictionary between a theory of gravity in his all right 1 d plus 1 dimensions, the bulk, and a quantum field theory living on its dimensional boundary, the CFT. Bulk black holes match thermal states in the boundary theory. Bulk geometry corresponds to patterns of entanglement across the boundary. For our question, the delight is also the puzzle. If a fully 1 d plus one-dimensional world with gravity can be exactly equivalent to a dimensional world without gravity, then the number of spatial dimensions may be dual, a choice of language rather than a unique feature of reality. The extra dimension in adds can be viewed as a scale in the boundary theory. Moving in the radial bulk direction corresponds to zooming in or out on the boundary. Dimension becomes a direction in the space of descriptions. Does this apply to our de Sitter-like universe with positive vacuum energy? We don't have an equally polished dictionary there, but the moral likely survives. Knowing the count of spatial dimensions may require specifying the frame of description. In one frame, 3 are extended, others are hidden. In another, an extra direction is nothing but renormalization flow in a lower dimensional theory. Truly, in this view, is not about a fixed inventory. It is about the invariance under change of description. When space emerges, take a deep breath and read a sentence that once sounded absurd to working physicists. Space may be emergent from entanglement. It goes like this. In the adds divided by CFT dictionary, areas of minimal surfaces in the bulk correspond to entanglement entropies of regions in the boundary. Stitch the boundary degrees of freedom with a particular pattern of entanglement, and you weave a bulk geometry. Tear the pattern by reducing entanglement, and the bulk pinches or disconnects. The geometry responds to information like a sail to wind. The math behind this has blossomed. Tensor networks such as MERA, multi-scale entanglement renormalization ansatz, produce webs that look like discretized versions of hyperbolic space. Quantum error-correcting codes implemented in a holographic layout explain how bulk information can be robustly stored on the boundary. ER equals EPR, a slogan conjecturing that entangled pairs, EPR, are linked by wormholes, Einstein-Rosen bridges, reframes geometry as a gift that quantum entanglement gives to gravitation. If the room you stand in right now is, at its deepest, a story the universe tells itself about how its degrees of freedom are entangled, then the question, how many spatial dimensions truly exist, shifts once more. It becomes, how many independent directions of entanglement does the code support? How many layers of scale are needed to reconstruct the physics we see? The answer could still be 3 extended ones. But the reason is not because God poured space from a 3-spouted teapot. It is because the quantum microstate of our universe knits together in a way that supports 3 macroscopic directions. Dimensionality that flows. Not all roads to quantum gravity run through strings in holography. In causal dynamical triangulation CDT, spacetime is approximated as a sum over many simple geometries, triangles, tetrahedra glued together, respecting causality. Remarkably, when you ask a small, diffusing particle, how many directions can you wander? The answer, the spectral dimension, seems to flow. It is 4 at large scales, 3 space plus 1 time, but drifts toward 2 near the Planck length. In asymptotic safety, a certain fixed point behavior of gravity's couplings likewise suggests a reduction in effective dimension at high energies. This is not the same as extra hidden hallways. It is as if the texture of the walls themselves changes with scale, offering fewer independent ways to get lost when you press your nose against them. It softens the infinities that plague quantum gravity. Fewer directions at the smallest scales means fewer ways for integrals to blow up. For the questioner who wants a number, this is exasperating. For the theorist, it is a clue. Dimension is not a monolith. It can be a running property, like a coupling constant, telling you how the universe behaves as you zoom. 3 spatial dimensions may be a large-scale phase, stable and generous to life, while the deep ultraviolet tells a leaner story. Branes, boundaries, and confinement. If extra dimensions exist, why don't electrons wander off them? One answer is confinement. Fields may be trapped on a defect or brane, much as sound can be trapped on the surface of a drum. In some constructions, scalar fields generate a domain wall in higher dimensional space. Fermions then localize on that wall because their equations tie their fates to the scalar's profile. Photons can be stuck via different mechanisms. Gravity, being geometry, is more promiscuous, feeling the whole bulk, but warping can focus its influence near the brain. This gives another experimental guiding star. If matter is tightly confined, but gravity leaks slowly into the bulk, then gravitational waves, ripples in spacetime, might disperse or decay in ways that slightly deviate from general relativity's predictions. The discovery of gravitational waves was a bonfire lit in a dark field. Now we can watch how the flames flicker. Do the waves arrive with the expected speed and amplitude? Do black hole ringdowns, the dying echoes of a merger, match the quasi-normal mode spectrum of 3 extended spatial dimensions? So far, the notes align with 3, but the era of high-precision gravitational wave spectroscopy has barely begun. With more events, the spectral fingerprints of dimensionality, if they differ, could come into view. Life's geometry. It is tempting to treat anthropic arguments as gauche, but they are part of the portfolio. Newtonian gravity in spatial dimensions behaves as 1 him. Ape is pro 1 divided by r n1. Stable, closed orbits like ellipses are a happy property of his no 3 n equals 3 n x 4. N is greater than or equal to 4. Generic bound orbits precess wildly or destabilize. In id 2, n is less than or equal to 2. Gravity loses its familiar binding character. Chemistry's choir sings with 1 hasn't there. 2, 1 divided by r, 2. Electrostatics, atomic orbitals, and the chemistry of carbon that supports life as we know it are delicately tuned to that geometry. The world can be hospitable in 2 senses: hospitable to our equations and hospitable to beings who write them. 3 extended spatial dimensions seems friendly on both counts. Yet be careful. That argument can explain why we are here, not whether extra curled dimensions are also here. A house can have a cozy living room and a labyrinthine attic. You inhabit the room, you only hear the attic when it creaks. The effective field theory view. Don't overfit reality. A philosophical sobriety check. Much of modern physics is scaffolded by effective field theory. EFT. It says, roughly, at a given energy and length scale, describe the degrees of freedom that are active and integrate out the rest. Keep the symmetries and write the most general Lagrangian aloud. Organize ignorance in a series of operators suppressed by whatever heavy scale you haven't reached. EFT teaches humility about fundamental claims. Ask, how many spatial dimensions truly exist? And EFT replies, at your scales, 3 extended ones. Full stop. If there are more, they are either too heavy to matter or too sly to show up. It is a defense against overfitting. The world is not obliged to reveal all its UV secrets in your IR data. But EFT also empowers the hunt. It tells you how extra-dimensional physics would bleed into low-energy observables as particular higher-dimensional operators with coefficients you can bound. Every improved measurement tightens the EFT vice, which either crushes the exotic into a corner or leaves a gap for it to breathe. Progress is the closing of loopholes, dimensional illusions in the lab. Part of the joy of physics is its fractal self-similarity. Ideas repeat in different clothes. In condensed matter systems, emergent quasi-particles live on effective geometries. In a strong magnetic field and low temperatures, electrons in two-dimensional sheets create the quantum Hall effect, an integer quantization that suggests the system's deep description knows about a lower dimensional space, while semimetals host excitations that behave like relativistic particles in reduced or tilted dimensions. Cold atom lattices simulate holographic dualities by engineering interactions that mirror those of field theories, letting us toy with bulk divided by boundary correspondences in tabletop kits. None of these lab marvels prove that our cosmos has extra spatial dimensions, but they normalize the idea that dimension is a contextual property. If a crystal can host an effective universe of fewer or different dimensions than its atomic lattice, why not the cosmos with respect to its quantum microstructure? The lab becomes a grammar school for concepts we fling toward the sky. Boundaries, walls, and what counts. Counting dimensions sounds crisp until you ask what you're counting. The number is cleanest when you count extended dimensions that macroscopic rulers can measure 3. It gets interesting when you count compact dimensions that are too small to see directly possible with responsibilities. You must specify their size and shape, topology, because different shapes produce different physics. It gets slippery when you count effective or spectral dimensions, properties read off from how fields or random walkers behave, which can flow with scale. It gets metaphysical when you count dual dimensions that appear in one description but not in another. The ad's radial coordinate is as real to a bulk geodesic as the renormalization group scale is to a boundary practitioner. So what counts? A workable answer is operational. A spatial dimension truly exists to the degree that it offers independent directions that some conceivable probe can traverse or some observable depends upon. That definition is not perfect. It privileges measurement, and the very notion of a probe depends on the theory, but it keeps us honest, tying existence to testability without dismissing the power of dual pictures. It also aligns with how physicists quietly behave. We build what we can, model what we can't, and try to make both stories meet. A scorecard we can read. It's helpful to keep a mental scorecard not of winners and losers, but of constraints met and predictions pending. 3 extended spatial dimensions, strongly supported by gravitational tests, planetary motion, satellite dynamics, GPS timing, and daily engineering. If a 4th extended spatial dimension existed at human scales, it would have rewritten every map we've drawn. Compact extra dimensions, string scale. Theoretically natural in string divided by M theory, current experiments do not rule them out if their sizes are tiny, Planckian, or slightly above, and couplings to standard model fields are appropriately suppressed. The landscape, the many possible shapes and sizes, remains a wilderness of options. Phenomenology tries to fence trails through it. Large or warped extra dimensions, ADD divided by RS, constrained by sub-millimeter gravity tests, collider data, astrophysical cooling bounds, and cosmology. Not dead, hemmed in. The parameter space, still alive, is clever and specific. Emergent divided by holographic dimensions, conceptually robust in ADS divided by CFT, experimentally indirect for our universe. However, their explanatory power in disparate arenas, from quark-gluon plasma to quantum error correction, makes them hard to ignore, and they may be essential clues to the nature of spacetime. Running divided by spectral dimension, an attractive feature in several quantum gravity approaches with suggestive mathematical results. Experimental handles may come from Planck scale imprints, which are subtle, dispersions in high-energy photons, minute anomalies in gravitational wave propagation, or delicate deviations in early universe observables. All challenging, all on wish lists. No line on that scorecard feels like a slam dunk of certainty beyond the first. But physics rarely offers slam dunks outside of domains where precision is king. Instead, it offers convergence, different instruments, different lines of evidence, all pointing to the same neighborhood on the map. The human angle, how we perceive, how we err. A brief interlude about us. We evolved to throw spears in parabolic arcs and to judge distances by how fast a tiger's stripes grow on the retina. Our inner cartographer assumes Euclidean space. Our language breaks when asked to fold a torus or visualize a Calabi-Yau manifold. Mathematicians learn to draw with algebra and topology. Physicists learn to trust those drawings even when the eye protests. That bias matters. Our sense of what is natural 3 dimensions, inverse square forces, smooth manifolds, was reinforced by survival, then by enlightenment, common sense. Each revolution, non-Euclidean geometry, relativity, quantum mechanics, gauge symmetry, has asked us to doubt something deep. Extra spatial dimensions ask too. It is not that common sense is wrong. It is provincial. The modern discipline is to acknowledge the provincialism and then demand payment in predictions. If you ask my belief, I keep it on a short leash. If you ask my bet, I place it on data, the edge of the page. Every map has an edge. For us, it is the Planck length, 1.6. 10 ems, 35. 1.6 times 10, 35 meters, and the energies near 10, 19, 10, 19 GeV. Our experiments are continents away from those scales. In that gap, theory plays. It invents spacetimes with 10 or 11 dimensions, branes and fluxes, lattices of simplices, group fields, spin networks. Some of these toys become tools, some remain playthings. How do we keep score? By consilience. Theories that solve old problems without breaking what works earn credit. Can extra dimensions soften the hierarchy problem? Can they explain why there are 3 families of quarks and leptons? Can they incorporate dark matter naturally? Can they keep flavor physics clean? Can they pass precision electroweak tests, cosmic microwave background fits, structure formation constraints, and gravitational wave observations? Can they do so without Rube Goldberg machinery? By novel predictions. Theories that invite new kinds of experiments are precious even if those experiments fail, because failure prunes the tree. Propose a resonance spectrum? Go look. Predict missing energy distributions? Go look. Suggest a dispersion relation for gravitational waves? Go look. Offer a distinctive black hole ringdown? Go listen. By unreasonable effectiveness across fields. Holography, for instance, was born in gravity and now informs condensed matter and quantum information. When an idea pays rent in multiple neighborhoods, trust it a little more. The verdict, earned, not assumed. So, how many spatial dimensions truly exist? At human scales and across the breadth of precise measurement, 3 extended spatial dimensions. This is not an assumption, but an observation tested every day by satellite engineers, surveyors, chemists, and by the gentle swing of a pendulum. If this book were an almanac for navigators, the entry would end there. At microscopic scales still beyond our direct reach, the universe may host additional compact spatial dimensions whose sizes and shapes tune the particle spectrum. They would be as real to a graviton as a guitar's thickness is to its harmonics, even if our fingers only glide along the strings. Whether they exist is not a matter of taste. It is a matter of bounds and future discoveries. Current data fences them. It does not banish them. At conceptual depth, the count of dimensions can be dual and emergent. A world with gravity can be recast as a lower dimensional world without it. Geometry can arise from entanglement. The effective dimension can flow with scale. In those frames, asking for a single, eternal integer is like asking a coastline for its length without specifying your ruler. The right answer includes the ruler. If you want 1 line to carry into the night, carry this. 3 to live in, possibly more to live under. And in the end, dimension is as much about how the world is stitched as how it spreads. The door we promised. Back to the room. The one with the invisible walls. You set the book down, or, if you're listening, you let your attention return to your breath and you look around. 3 directions you can walk. You can touch the plaster. You can feel the floor. But the door we promised is there, if you learn to see it. It's in the fact that gravity is geometry, not force lines on a background. It's in the way information resists being copied, how entanglement refuses to be local. It's in the way black holes count their states as surface, not volume. It's in 1,000 accelerators and a few clanking torsion balances. It's in the spectral map of the infant cosmos and the chime of distant black holes merging. Open it, and there may be a tight spiral staircase of compact dimensions, a warped corridor that stretches distances unevenly, or a mezzanine built of entanglement, where up means zoom out. Or perhaps the door leads to a balcony from which you can see that your room is part of a larger house, but that house is drawn on the boundary of something even stranger, and between them is a dictionary, not a doorway. This is not a capitulation to mystery. It is a celebration of how far we have come, from a room to a manifold, from a force to a curvature, from a count to a code. And it is a pledge about how far we can still go. New detectors, new surveys, new ideas that make audacious claims and then kneel before the data. If you are making an audiobook and you asked for one, here is your closing cadence. Tell your listeners that the universe gave us 3 spacious freedoms so that stars could swirl, atoms could bond, and brains could dream. Tell them it may also have hidden more directions in its trim, secret places that bent the rules to keep gravity humble and particles diverse. Tell them that even if space is a story we tell with entanglement, it is the best story we've ever told. One with characters called measurements and plots called predictions and a narrator called reason. Then tell them this: we live in 3, we wonder about more, and we build instruments to turn wonder into knowledge. That is the human dimension, the one we add to the universe just by asking the question and daring to demand an answer. And with that, the lights of our room dim. The walls do not close in, they wait. The violin on the table hums softly with the air's tremor. The night beyond the window is a manifold of possibilities. Somewhere, very far or very small, a graviton tests the trim. Somewhere, information ties a new knot, and a patch of geometry swells from it like a tide. Somewhere, a detector catches a whisper that refuses to fit the old scores. When that happens, the count may change. If it does, we will change with it, adding a hallway to our house, a chapter to our book, a direction to our dreams. For now, 3. For now, a promise. For now, a door.